We're gonna start. You wanna grab something quickly, go ahead. I'll start with introductions. So first, let's talk about the schedule. We'll discuss right now the FAQs, like how does it work. Then we'll have 3 presentations. One, Kafka at GitHub, challenges and future directions. One from ORB, revenue alerting at scale. And one from Redpanda, streaming data enrichments and analysis with Redpanda, CDC and Python. Basically, the talk will go for 30-35 minutes, and at the end you can ask questions. If you want to ask questions, please raise your hand, and somebody will give you the mic so people online can hear you. Sounds good? All right. Let's start with introductions. My name is Boris Shkolnik. I work here at LinkedIn. I'm managing a control plane group for stream processing. We do stream processing at scale, as you can guess, mostly based on Kafka, and using Flink and Samza for actual processing of the data. My co-host, Beckett, not ready.
Hi, folks. I'm Beckett, and I'm also on the LinkedIn streaming team, mostly working on Flink. Thanks, guys, for coming. Yeah.
And we have a third person, Efe. Efe, can you present yourself?
Hi, everyone. My name is Efe. So I am a manager at LinkedIn. So I'm one of the co-hosts. Welcome.
Sounds good. Thank you. All right. So this is the schedule. All the everything will be recorded and later posted on YouTube on the LinkedIn Engineering. And the meetup event site will also have the link for the recording. Those who are on call, if you want to ask some questions, just go to Q&A of the webinar interface, enter your question, and at the end, either me or Beckett will read the questions to the presenters. In the future, if you want to present, post a message on the meetup or send a message to us either through LinkedIn or through email. Any questions? No, let's start then. So our first presenter is Eric Sun from GitHub. The presentation is Kafka at GitHub, challenges and future directions. Eric will discuss how Apache Kafka is used. Eric, you want to join? Sorry. So Eric will discuss how Apache Kafka is used at GitHub to power features through event streaming and background job processing platforms. There are specific design trade-offs, challenges in scaling these services, and what future holds next for the platform team. Eric himself brings 10 years of experience on platform teams to data pipelines team at GitHub. The group oversees the messaging platforms that connect GitHub applications and data stores for millions of developers worldwide. And pay attention to this. Eric enjoys working on performance problems and specializes in incident analysis and remediation. Please go ahead.
So today I'm going to talk about how we use Kafka to bring that messaging platform to GitHub services, some challenges we run into while operating Kafka, and also some of our future plans to address those issues. And at the end of this 30 minutes, hopefully you'll have a better idea of how to manage your Kafka clusters more smoothly, if that's what you do. Okay, so what does Kafka power at GitHub? Pretty much every major feature you use depends on Kafka in some way. So I'll talk about a simplified use case that's common or typical. If you push a commit to a repository, you want to reuse this data. So maybe you'll publish an event for it called a commit push event. And then, you'll have a bunch of consumers that are going to do a bunch of different things. One might update all the pull requests associated with that commit. We might do some counting over the event stream. And, another consumer might do triggering of actions runs. And all these things will happen in parallel. So another use case we use it for is to parallelize call graphs. So a typical example of this is when you make an HTTP request to the GitHub website, we may emit a bunch of events, and each event will essentially be processed by a Kafka consumer somewhere else. And so that'll happen asynchronously. And this type of work is so common that we've actually built a background job queue service called Aqueduct around this that serves about 4 billion background jobs a day at GitHub. All right, so what does our team actually do? We provide two major services to GitHub. So one of these products essentially is called Hydro Kafka. And really what it is it's an entire ecosystem around Kafka that includes schema enforcement, cluster management. So we provision the brokers for you, and then you can write your own producers and consumers. And we also have a lot of self-serve tooling to help you debug your consumers. And so, yeah, it's a little bit typically harder to use because, you have to touch Kafka itself. And the other thing is what I mentioned is Aqueduct. It's like a queuing system similar to SQS. And it's a little bit easier to use because you're just interacting with a REST API instead of Kafka consumer groups, semantics, and producers. So the first thing I'll talk about is something called the Hydro Schemas repo. So it's just a Git repository that contains all of the schemas for all of our topics. And if you want to add a new schema, you just create a pull request, add it. You run a bunch of linting on your protobufs to make sure that you're not introducing any backwards incompatible changes. Also making sure that for any topics that you've hooked up to the data warehouse, that you're not messing up the resulting tables. So that kind of protects the topics from bad deserialization issues. And then we serve all this as static content over Nginx. So it's kind of similar to like the schema registry in a way, if you use that. And so this is kind of what it looks like when we put events in a topic. There's an envelope and it contains information about the schema that you're supposed to encode your message with and the encoded message. And our clients all know about how to use these, so they can do, so we have native clients for Ruby, Golang, and the official Java client. They're all just wrappers around other Kafka clients. And for any languages that are not supported there, we have something that allows you to produce to an HTTP gateway, and you can tell it the protobuf schema, and it'll do the serialization for you, and you can consume it somewhere else. So here's an example of some of the tools we offer to our developers when they're trying to troubleshoot things. So if you're using the Kafka command line interface to see what topics are in a cluster, or you want to see what consumer groups are there for each topic, this is all self-serve. You can do advancement or resetting of offsets if you need to manage your consumers. And we also provide kind of advanced metrics similar to Burrow, which is a monitoring service. So we also emit metrics like consumer lead time and effective retention to tell you how much time you have to read messages, before they're written by the head of the log. Okay, so next what I'll talk about is Aqueduct, our queuing system, background job system. So at its core, it really consists of, a REST API that lets you send jobs to a queue and also have workers that receive these jobs from a bunch of queues. You get one back, and then you can heartbeat it or acknowledge it to let the job system know that you're done processing. And this is all built on top of Kafka. So originally, we built this to replace Rescue with a fault-tolerant and durable solution. And it has a bunch of features like we can schedule a job to be delivered, a week or two in the future. If you have a worker that crashes while processing a job, you can redeliver the job. it'll do it for you. We emit a lot of rich metrics like processing times for all your queues, the round trip time, delivery time when you publish and receive a message on the queue. And with that, you can even do per queue throttling. So you can pause queues. You can do things like processing time quotas so that, you know, a bunch of workers trying to pull messages from a bunch of queues don't run into starvation issues. And you can also enforce explicit rate limits. And one key thing we really wanted this to do is to be easy to scale horizontally. So how do we do that? So I'll show you kind of how this works. When you send a job to Aqueduct, it goes to the API layer, and we create a ingest topic per queue. And so then after that, we have a bunch of consumer groups called the relays, which are responsible for reading these jobs out of the ingest topics and queuing them into a cache. And one benefit of this is that you can now decouple your worker concurrency for processing the jobs away from just the consumer count. So once we do that, it's considered queued, and every job state is actually tracked in a compacted state log topic. So that's like event sourcing. And by doing that, we can track the life cycle of every job that goes through the system. You know, we can query this topic through the data warehouse and follow it and see what happens to debug. And we have this thing called a state processor, which kind of scans through this periodically to see if jobs need to be repaired. And on the worker side, right, you're looking at jobs, you ask for some, or you ask for one, it gives you one, you heartbeat it to say like, hey, I'm still working on this. And then you finally say, I'm done, or, you know, this has succeeded or failed. Okay, so here's an example of us kind of exercising this whole ecosystem for Hydro. So we'll have some jobs in a queue that are redelivered more than once, and we're gonna go look for them for this queue. We're gonna pick one of these jobs by job ID, and then we're gonna run a second query against the data warehouse to see basically everything that happened to it. So there you can see all the timestamps, all the job states, additional metadata about what partition it went to, and also client IDs about who it was processed by. Trying to advance to the next slide. Just gonna put this. Okay, great. So we built all this awesome stuff, and it just works all the time without problems, and I have absolutely zero stress in my life. Great. I wish. So the first challenge I'm going to talk about is developer support. So our team spends about 25% of our time just having technical discussions, talking about trade-offs with our developers. And even though we write a lot of extensive documentation on how to like use Hydro Kafka or use Aqueduct, the background job service, it's just, you know, not a replacement for actually talking to developers and giving them architectural advice. We get a lot of questions like, how do I do X with Kafka? And oftentimes you have to walk the conversation back a little bit and say, okay, like, what are you trying to do? And, you know, maybe Kafka is actually not the best tool for you. And because of this, you know, we can avoid a lot of types of problems like bad workloads in the clusters because we're an approachable team and we like our developers. And we're not just like, go read the manual. So in addition to that, we also have to do a lot of operational support. So if you're using Kafka, you're running your own consumer groups, it can get a little bit tricky. So I've probably spent like 5% of my lifetime on this webpage. It's hard to run consumer groups. It can be hard for us. So for our developers, it can be extra hard. So you can set sensible defaults, right, for these settings, of which there's like 50 something, but you still have to worry about like 12 of them, right? You have to make sure you're not pulling too many bytes in so you don't run out of memory, right? If you're processing things too slow, you don't want to time out and have a rebalance. Figuring out how the messages are actually fetched in parallel, it's just like a lot of details. And remember, we have to know how this is implemented in 3 different languages and libraries. So it's just a lot of work. And this is just on the consumer side, not the producer side. Okay, the other half of challenges we deal with is the actual management of Kafka clusters. So we've gotten here after 6 years without cruise control, which has not been easy. It's been very challenging. And as a result, what I'm going to do next is share some fires that we've seen in the wild, and what we've learned, and also you might learn some tips, to help you with your cluster administration. And yes, the dog is me. Okay, so just like how people always say you don't want to put all your eggs in one basket, you don't want to put all your partitions on the same broker. That's problematic for a lot of reasons. One reason is contention, right? Get contention, tail end latency shoots up. Something even worse is when the broker goes down, right? You'll see produce delays due to replication lag, they're waiting. Even worse is if you're waiting so long for the broker to come back, and suddenly it does, and it like tanks the throughput on your cluster because it's trying to catch up to all that replication lag. So yeah, big brokers are just not good news, especially if they have like a lot of high throughput partitions. So something that we're trying to do there is just preemptively throttle under replicated partitions, especially if like a broker is going to be out of service for a while, then you can kind of avoid that hit and penalty. All right, speaking of slow things, slow and lazy brokers are also bad news for a cluster. What do I mean by lazy? These are brokers that don't have any particularly exciting workload on them, but yet they still manage to behave very slowly and just do weird things. So they might do some things just fine, and they might do some things horribly. So we had like a 40-minute outage once where a group coordinator caused constant rebalancing for 40 minutes. A reminder for those who are not familiar with what the group coordinator is: when you run a consumer group, the group coordinator is responsible for managing like liveness of the consumers and propagating the partition assignments for the consumers so they know what to work on. So if it's not behaving well, and in this instance, we saw that its network threads were completely saturated, even though it's getting like no traffic. All the consumers trying to heartbeat, so they would stabilize after joining, and then they'd get kicked out immediately because the group coordinator is actually too slow to process all the heartbeat requests. Or vice versa, the consumers are like, I haven't heard from you in a while, so I'm going to leave and come back. And so this just loops over and over again. And it didn't get fixed until we just kicked this broker out of the cluster, and got reelected, and it worked just fine. I wish I could say that was our only horror story with constant consumer group rebalancing. But sadly, it is not. So starting from November 2023 of last year up until June of this year, Aqueduct, our background job service, actually saw job start delays of several minutes, a few times a day. And this is obviously very problematic for our workloads because a lot of our users are expecting 30-second delays. And most of the time they see something like 250 millisecond delays. That's like a typical P99 over a 10-second range. So yeah, a lot of teams are unhappy at us. Everyone's getting paged. So the reason for this is that the relays, when we first built this thing, we only started it with one consumer group that's responsible for reading all the queue topic partitions in the cluster. So one global consumer group. So if it's rebalancing, no new jobs can be processed because it can't read them and make them available to workers. It's bad news. So this actually took us 10 days to get to an initial mitigation. And this happened over Thanksgiving break because of course. And I'd like to talk about why it took us so long to get to an initial mitigation other than Turkey. Okay, so when we first saw this problem, it actually happened last August, but it only lasted for about 30 seconds. We had no clue what was happening because there were no errors. Nobody was leaving or joining the group. And we just saw a constant stream of info level logs saying, preparing to rebalance. All right, great. So we did some source code diving, turned up the logging levels and all the group coordinator stuff, and we waited 3 months until it happened again. And then when it started happening again, sometimes it'd recover in 15 seconds, sometimes it'd cover in 3 minutes. It was all over the place. All right, so finally happens. What's wrong? We searched the debug level exception, and there's only one result. And sadly, there's no Stack Overflow answer for this one. So we have no choice but to go over the 60,000 lines of code that comprise the group coordinator, the consumer group rebalance protocol, the produce path, how replication works, because that's all involved in this problem. So I'm going to explain what that timeout exception means. Basically, what it was saying is that when the group coordinator is trying to replicate the assignment message, so these are the partition assignments for the consumers, it's taking too long. Every consumer group is mapped to one consumer offsets partition, and it just wasn't getting through to either of the replicas. And so we still had no idea what was going on, so we needed even more debug data. Okay, imagine this, it's 4 a.m. All of a sudden your pager goes bap, 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 bap. And then, everyone in your house is awake now, they're mad. You're mad. Your eyes are crusty, you can't even, put your glasses on or whatever, get to the computer. And then you realize that you can't even do anything because the rebalancing issue has already fixed itself. So you can't do anything like run a heap dump. You can't collect flame graphs. You have no useful actions to do. So now you're like extra mad. So this is a problem for us. So we had to write the tooling to automatically profile and do diagnostics on this replica set. Only when we saw this infinite rebalancing thing happen. So that took time. Okay, so now we have flame graphs of what's going on here. What's going on? So all we could really see is that the fetchers on the replicas were stuck waiting for a response. The remote times from the produce latency were actually very short. So it's not like we were waiting 30 seconds or 3 minutes for this response to come back. The flame graph showed that we are actually getting responses. So we figured maybe these responses are just empty. So we looked in the code again, and now we're deep in the replica fetcher code. And it turns out that you can get an empty fetch response if your data is not going to fit within the max fetch response size. So ours was configured to 10 megabytes, but guess what? Our group assignment message is 18. So it's going to get skipped most of the time because there's other partitions co-located on this replica set. All right, so just increase it. Problem solved, right? It did get a little bit better, but this problem did not go away. All right, whatever. Let's just remove contention from the equation altogether. Let's isolate this partition away from all other topics and even replace the hardware underneath. Still no dice. We called the mothership to get us in contact with LinkedIn. We talked to the Kafka team, and they basically told us, yeah, we have bigger groups than yours, larger than 18 megs, but we still don't see this problem. All we can really say is that your group coordinator is really screwed up. All right, let's go back to the oldest trick in the book. If it doesn't work, turn it off and turn it back on again. So actually, one of our most effective mitigations was just to restart the group coordinator after 40 seconds of rebalancing. And amazingly, this capped our rebalance times to a minute instead of varying from 3 minutes to 15 minutes or infinity. And most of the teams actually stopped screaming at us. So for whatever reason, this made the message available to replicate. Now, obviously, this is not a long-term solution. And also, we had to do other things like prevent all rebalances from happening as much as possible. So we had to defer metadata updates like queue creations, deletions. We couldn't restart stuff whenever we wanted to, so we'd have to move it all to off-peak hours. It was a lot of pain for everyone involved. So the approach that we ended up going with is, well, we know that it's definitely related at least partially to the message size. So let's try to get it down. So what we did is we ran a bunch of tests, performance tests, and we doubled the amount of partitions in the test cluster with 2x the amount of partitions in our production cluster, which is about 6,000. So we tested with 14,000 partitions. And then we put in 150 consumer groups to read this data. And we went from an 18 megabyte message size to about 32 kilobytes per message size. And we also were able to cap our rebalance times consistently to 5 seconds. down from like minutes. And this also has the added benefit that when a consumer group rebalances, only a subset of all topics are affected, not just, so that's good. Okay, so what did we learn? It's a good idea to understand how the system works underneath before you're in an incident. One way to do that is to, periodically run, flame graphs against your brokers to see what they look like when they're actually being good and healthy. Then when you run this kind of diagnostic automated, when they're unhealthy, it should be pretty easy to spot like a stark difference in what the brokers are doing. In addition, right, you want to do things like conditionally turn on extra like high level logging, like debug or trace, but only for short periods of time on very targeted classes. And you don't want that to be a manual process. Logs are extremely important. Really try not to lose any of these broker logs because, one log line could make or break your investigation. And again, it really helps to have a lot of cluster metadata tools to help you see like what's located where and to be able to move data around. And so we have a lot of tools around the admin client that let you move data around the cluster. Okay, something else that helped us is we generate synthetic traffic into our production clusters. So we emit things like, base produce to consume latency. And that's one of the things we alerted on to tell us that this type of infinite rebalancing thing was actually happening. I'm not going to spend too much time talking about all of the metrics you can monitor that are emitted from the brokers, but you can find all of them in this docs ops HTML file in the broker source. And from there, you can see like basically what they mean. You can look in the code to see how these metrics classes are used and kind of really develop an understanding of, how the critical paths work. Okay, coming to the final section here. One of our biggest challenges is trying to figure out why things are slow. So workloads vary from broker to broker, right? Access patterns vary. They can vary from cluster to cluster, especially if you have a lot of topic partitions. The default metrics are not by partition. So you'll see produce latency spike, but you're not sure exactly what's causing it. How do you know if it's workload versus like a hardware issue? These are all things that we struggle with. I would say that almost all of our performance problems come from uneven partition placement, which should not be a surprise to anyone because we're not running cruise control. We're like manually rebalancing the cluster on every on-call shift, right? Based on, whatever happens, good or bad. We're really trying to reduce our broker data size. So we started out with 2 weeks of retention to make sure that, we could debug things in time. We're cutting that in half, right? And that should also help with things like big brokers dying and coming back. Our provisioning process for new brokers has traditionally been very painful. You'll press some buttons, wait 40 minutes, and it might not succeed at all. So we're really trying to use tools like Temporal to automate this workflow. So you can press a button and just get like 40 new brokers if they're available. And finally, we want to use cruise control. So that's a work in progress, and I'll talk about that next. In addition, so for the future, we want to make sure that we can stop those bad or lazy brokers really quickly because they just cause a lot of great failures. So that means improving our integration with hardware health endpoints, writing better health checks to find out if problems are actually workload related or not, so we can nip it in the bud. We're starting to split up some of our large general purpose clusters, like kitchen sink type clusters. So we might designate clusters now as like being low latency, which means that the brokers can't be completely utilized. And finally, for cruise control, which is our biggest endeavor that's coming up next, is how can we choose goals that will make it so that our data is always perfectly shuffled around and, we're not constantly crying from slowness. So to choose goals, I think the first thing we need to do is establish a good performance baseline. So for example, if we're targeting a produce to consume latency of 100 milliseconds, actually in production, we don't know the exact workloads, or if we even have the right broker configs set up that, like what workloads actually cause us to violate this SLO. So in the past, like we don't even know like if the network utilization is fully utilized on our brokers, because a lot of our broker configs are the result of tuning over time ad hoc in response to incidents. And we've traditionally lacked like a performance environment to make these changes. So we would do things like gradual config rollouts and rollbacks, but this is becoming increasingly untenable because these changes are very risky, and more applications depend on us for critical workloads. So what we're really trying to do here is build like a really fancy, well, maybe not fancy, like stress test suite where you can change different variables one at a time and eliminate a lot of the loss of control you would have in a production environment. So iterating over things like the broker thread counts, replica fetchers, various fetch batch response size configs, producer and fetch concurrency, all that stuff. And then you can finally say, oh, okay, we break at this point. Let's feed in 80% CPU utilization and cruise control and have it rebalance then. Okay, is there any way we can stop even more future suffering? You could try present suffering. I would encourage so this is something we're going to do, but these are all scenarios that we've seen and maybe you've already seen. And the idea here is to figure out how quickly you can actually detect that this is happening in your system. Is it doing something bad? And also realistically, what can you actually do in response to this? So running drills will help increase your incident preparedness. So yeah, I think we've done a pretty good job this past 6 years of getting to where we are. Obviously, we can do better, but I think a lot of our success comes from just being really meticulous about doing incident write-ups. We're very honest about things we do know and what we don't know. And we always we do a pretty good job of writing about like why we do things. So I could almost go back 5 years and tell you, in some issue, like why we chose to do something a certain way. But last of all, it's really just a lot of hard work. There's no magic here. All right, that's all I have for today. And hopefully you learned something about running Kafka clusters a little bit less painfully, and you'll have a lower blood pressure value when you run to your next incident. Thank you very much.
Thank you, Eric. Any questions from the audience?
Hi, I'm Crit. You mentioned you like briefly went over a slide that like had your scale of stuff. What's your typical like hardware broker? Do you run in the cloud? Do you run on prem, or how much data do you put on a broker?
Yeah, so we run on both on-prem. So we have our own hardware, and we also run on Azure as well. Going back to the slide, I think we have about like 430 terabytes total right now. I can go back to it, but I guess that's like the amount of data we're working with. Did you have like a specific question about?
How much data per broker?
Okay, so when we first started out, I think we started out with like 6 terabyte brokers, but now we're kind of like experimenting with the size. I think mostly what we're doing now is, so I mentioned that we're trying to reduce the retention just to get like data that doesn't need to be around, like out of there. But yeah, I would say most of them are about 6 terabytes per disk, and we're trying to go more downwards. So one approach we're exploring might be more smaller brokers, right? Problem with that is, like you need the hardware. So that's also like a capacity issue we have.
Any more questions? I think we have one online question from Raj. Kafka provides at least one processing, and Aqueduct is built on Kafka. What happens if 2 consumers of Aqueduct receive and begin processing at the same message?
Yeah, so Aqueduct, because it's built on top of Kafka, is also at least once. But we do ensure that, so yeah, you can actually get duplicate processing at the same time. But the idea is that one of the jobs can, since we track the job state, you need to make sure that your workers are doing idempotent things. But generally, we observe that we don't get too many duplicate jobs. But yes, it is possible.
All right. Thank you. Anybody else? No? All right, thank you, Eric. We will switch the next presenters because the people from org got delayed a little bit. So Redpanda will go next. While you guys set up, I'll introduce you. So the topic is streaming data enrichment and analysis with Redpanda, CDC, and Python. Learn how to utilize streaming data platform to facilitate real-time data enrichment from monolithic databases into modern streaming architectures. We leverage the Bezium for change data capture and explore the development of Python-based services that subscribes to this data for real-time processing and applies machine learning to perform sentiment analysis. To show a practical use of how data streaming and processing pipelines work in real life, the process sentiment data is then published on another topic, highlighting how simple this is to do with new advancement in streaming and ML. So Brian Wood will be the presenter here. He's a creative technology leader, passionate about driving positive change and leading teams on the journey of continuous improvement. Brian is inspired to deliver better product quicker through low friction interactions, automation, and seamless integration with product organization and stakeholders. Take it away.
Check, check. Hi, everyone. Thanks for having us here. Thank you guys for hosting it. And I'm going to dive in because I have a lot of slides to get through. There's me. Quick question. Anybody in the audience, is anybody using Redpanda? Heard of Redpanda? Anybody who's already, yeah? Awesome. Free shirts for everybody who's already using Redpanda. Also free shirts for everybody else. If you scan that, anybody, you will get you put in a little bit of information, you'll get an email, and then we will ship a shirt to you if you like. Gotcha. Sorry. This is the real one. Go ahead. Everybody got it? Let me know. Give me a thumbs up when. All right. Good to go? All right. I'm gonna move fast. So quickly, as introduced, gonna give you all a brief introduction to Redpanda if you haven't heard of it before, just because it's kind of the centerpiece. Still gonna be using lots of Kafka tooling and stuff like that. And then we're gonna go through a bunch of Kafka, some tool examples and stuff like that. And then I'm gonna briefly introduce Redpanda Connect, which is a connectivity tool that we have in our portfolio. So just quickly, if anybody hasn't heard of Redpanda before, we're a drop-in replacement for Kafka, re-engineered from the ground up in C++. So it's a re-implementation of the Kafka API. We stand in the same place, serve the same purpose, all the exact same SDKs and or libraries and connectors and all the other tools all work seamlessly with us. And that's kind of our place in the market, right? Is to do Kafka, only do it a little better. Of course, we've got all the logos, lots of important customers, very impressive. Sorry, I'm moving fast because I want to make sure that I get through everything. So since our founder decided to sit down and re-implement Kafka from the ground up, he took the opportunity to make some design changes. Actually, kind of a lot of them, you know, some of the things that you guys were struggling with a little bit over at GitHub is Kafka's complicated, right? It's a really big distributed system that, you know, requires lots and lots of full-time engineers to run, especially at scale. And so when rewriting it from the ground up, one of the things that our founder Alex did was he took the opportunity to kind of change the way that coordination works. He implemented a raft situation amongst all the brokers where they're democratically electing leaders of partitions, kind of removing the need for an external system for consensus, right? Whether it's KRaft or Zookeeper or whatever. So it's a thing that's not there, right? The brokers continuously work together to elect leaders of partitions. And this also takes a role in how we automatically continuously rebalance your partitions, meaning that you don't have to worry about cruise control either. And also just because so many people are using, frankly, HTTP proxies and schema registries, each broker has one of those built in, right? So you can throw them behind a load balancer or whatever you want and interact with them and serve your schemas from there, because most Kafka implementations wind up having the schema registry eventually. So that's like a quick, breakdown of kind of like our lay of the land is significantly different. Our architecture is significantly different, but we're still standing in the exact same place. We still have a similar concept of brokers, and you would connect and configure all of your services in a similar way. I'm going to apologize in advance for the unlabeled graph, but the idea is that since we are a thread per core architecture, and we've re-implemented it from the ground up, as many of you know, Kafka is a thread pool architecture. Being Java, it has to stop all of your processes from time to time to do garbage collection. One of the major reasons that you see tail latency so high, rise at the end, right, is that your messages get caught multiple times often in garbage collection, meaning that they have to stop for hundreds of milliseconds at a time before they can be consumed. We don't have that problem. We rely on the C* framework to do our thread per core implementation, which means there are no stop all operations stopping all of your messages, which means we just have a much more predictable performance profile. You can saturate your hardware. This does come at one cost. You absolutely must have fast disks, right? Because we are actually going to all of the trouble. Actually, I'll jump ahead a couple. We are going to the trouble of writing to your disk on the leader of a partition, and also replicating to the majority of the participants in that partition group, so that when we acknowledge back to the producer that we have your record, we actually have it. I know it's a contentious topic on the internet, right? But if you aren't using fsync on all of your topics, or across your entire cluster, and you drop a broker, you can lose messages. And that's a thing that when we were deciding to rebuild Kafka from the ground up, we could not have, right? And it is a delineating, it's one of the things that makes us stand out. Financial organizations love us. But also we get the more consistent profile. All of these things are verified by Jepsen, right? They have gone through and verified our performance claims and our reliability claims and things like that. And they've also provided us with a suite of tests that we continuously test our product against. So that's the what makes us different, right? The footprint is different. We are more performant. We support greater throughput, lower latency. On a good day, we see lots of large clusters with producer to consumer, end-to-end latencies of 40 milliseconds or so in the cloud, which is usually pretty good for trading platforms and things like that, where latency is super, super important. So I'm going to jump into kind of the functional things that make us different, right? That's kind of the core of our product. But we also have a handful of features that kind of set us apart and make us behave differently as well. So one of the first ones is our tiered storage model works significantly different. I don't know if anybody's kind of keeps up on this stuff, but we do have recently in the Kafka ecosystem a concept of tiered storage has been introduced a couple of versions. Ours works significantly differently. So when you produce a message to your broker is then going to batch up that data on a time or a size interval and send that off to an S3 compatible storage, which means an entire copy, a fairly fresh copy of all of your data is sitting in your object storage. What this means is that we have that's very good from a now you're not limited by the size of the disk on your brokers, right? You can scale only for performance, and that's a great thing. But having an entire copy of your data sitting in object storage is good for other reasons as well. It gives us the ability, if you say you have like an asynchronous analytical workload, or you're training machine learning models, and you don't want to have that impact the performance of your production cluster, you can spin up a read replica cluster that is hydrated from that data that's sitting in your object storage. So that gives you a pretty, we have a customer, Poolside .ai is using that approach for training their machine learning models, because they retrain their base models very frequently. And this is saving them on the order of millions of dollars a year. This also enabled us to recently come out with a feature that we call whole cluster recovery. We have a completely managed offerings that are in the cloud. And you can, with a single command line, we call it RPK as our command line for our suite of tools. With a single command line, you can recover an entire cluster hydrated off of that data that's sitting in S3, and you can do it very quickly. Meaning, a lot of customers are in that scenario of, okay, they want some type of a DR strategy, and usually that winds up meaning that they spin up another cluster somewhere and they have Mirror Maker running or something like that, copying all of their data to another cluster. With whole cluster recovery, you can spin up a new cluster entirely hydrated by the data that's already sitting in S3. And as long as it meets your RTOs, right, you may lose some data during that lapse, right? But as long as that meets your RTOs, you have a recovery option that's better than nothing, right? Like I said, it's in AWS, it's on the order of like shy of an hour. We've tested it and the promises that S3 makes and the frequency that we batch the data into S3 gets it at about 48 minutes was the last time that we tested it. So anyways, kind of a free recovery option, right? We don't charge extra for it. It's just built in if you're using tiered storage. It's pretty great. So another thing we also recently built was the ability to do single message transforms on your brokers. We noticed that a lot of our customers are doing the very basic, like, hey, we need to convert from JSON to Avro, or we need to anonymize some data, we need to hash something or delete something, and we just want the product to fall onto another topic. We give you the ability. We have a WASM engine that we've built. I believe we also recently added JavaScript, so we've got Go and Rust here. But if you want to write a little function, you using RPK can push that function to your brokers, and your brokers will take that data as it's coming into your topic, perform that magic on it, and then push it into a subsequent topic. That's pretty cool, right? Because it's simple, but it also keeps the amount of latency that you're incurring down, right? We know a lot of customers will spin up Flink just to do something very basic like this. And that's kind of a heavy hitter, right? And then complicated and also introduces a significant amount of latency. I'll hopefully leave some good time for questions at the end. I imagine there's going to be some. We talked about high availability. We have the ability, like any others, to be multi-AZ. And like I said, we have some other replication options. So we've got essentially 5 ways you can get your hands on Redpanda. We have I'll start with serverless. We have some big clusters that you can, be multi-tenant on. They support, I believe, around up to 10 megabytes per second. They're cheaper than deploying your own cluster, right? Since it's shared hardware. We have dedicated, where we will essentially deploy a cluster on your behalf within our infrastructure, and then you can peer with us. This is a pretty common model, right, for other competing products. But we also have BYOC, which a lot of people wind up finding pretty advantageous, using the exact same automation mechanisms that we use in our dedicated offering. We can also deploy those into your cloud account if you wanted to run and have a completely automated service running within your account. We deploy a small agent that will be the kind of proxy that will deploy your cluster, manage it, maintain it, monitor it on our behalf. It will send some telemetry back to us. We have SREs who are watching it, making sure that your clusters are healthy. It's a very great way to keep sovereignty over your data. Compliance organizations usually are a big fan, and it gives you the ability to kind of bypass that whole concept of sending all of your data out to somebody else's network. We don't have access to any of your data throughout this course. We only have access to your metrics and telemetry. We have a community edition. You can spin it up right now. We have a quick start guide. You can Google it. It's just a Docker container that you can go in, or a compose file that you can spin up. And then we also have our enterprise edition, where you can, either of these, you can deploy via Kubernetes, or our Ansible playbooks are great. But the enterprise edition, there's a couple of small differences. The continuous rebalancing of your partitions, as well as tiered storage and some SSO features are only available in enterprise and not available. This is just a quick breakdown. I already kind of explained this, but the idea is that we have a control plane that your agent that's deployed within your account would be continuously polling for instructions, upgrades, monitoring, all those types of things. How am I doing on time? How much time do I have? Am I going until 7:15 or 10? What is it? Okay. One of our favorite customers, they're operating a fairly high throughput Lacework, processing whole 14.5 gigabytes per second across their whole cluster, or one of their largest cluster, I believe, quote, without breaking a sweat. But they're very happy. They have a lot of latency requirements, and they experience, out of all of our customers, probably one of the most drastic reductions in cost compared to the TCO of running Kafka on their own. So we're going to dive into the kind of the more technical material that I prepared. That's the introduction to Redpanda, some of the things that make us different. One of the things, so at the, let's see, I guess, how do I share? I was going to put another QR code in there back to the project. If anybody wants, I have a compose file with all of this stuff working, where if you want to actually like tinker with the different tools and parts and pieces and what we're about to cover, you can have access to that. But kind of the prompt is, thanks ChatGPT for the image. You know, we've got a lot of competing initiatives, right? Everybody's moving into or out of the cloud at full speed. You got microservices everywhere. You're supposed to be deconstructing monoliths, bringing real-time analytics to everything, and of course covering the latest AI and ML tooling and things like that. So I'm going to cover just some of the basic smaller things that you can do to make those things a reality, and just kind of a brief story, and we'll watch some data move around. Does anybody, just so I know how fast to move through most of these sections, is everybody kind of familiar with the BZM? Are people using doing CDC, stuff like that? Okay, I'll cover it a little bit. We've got some Python examples in here. Obviously, we just covered Redpanda. Is anybody using Hugging Face at all for ML stuff? Okay, cool. All right, I'm gonna try and move fast then. So given that prompt, I think WordPress is a great example of a monolith, right? It's a little bit, it's old. Not a lot of people are building brand new services with PHP, and it's got a relational database in the background. So what I did is I built a WordPress app, right, as an example of, or I deployed WordPress as an example of kind of a legacy code base. If anybody's not familiar with the BZM, it's a great tool for doing change data capture. It's a Kafka Connect implementation, so it's a plugin. If you were going to manage it, you would spin up your Kafka Connect instance. You'd throw a jar in a directory that has the BZM in it, and you would configure it using a task that looks like this. That is going to come. These are kind of the configuration details that are relevant. You're going to hook to your MariaDB. Here's the port. Here's the username and the password. And now all of the tables, right, that are being watched will now every time they change, any inserts, updates, or deletes are going to show up in topics as events. And one of the great things, I work with a lot of customers, right, who say, well, we can't do data streaming. We've got relational databases everywhere. It's too big of a lift. We can't get all that real-time advantage. This is a fantastic way to dip your toe in that water, right? So what I'm going to do, the example here is any comments that get left on this WordPress database are going to show up as events, right? And they're going to show up in topics, and we're going to do action, and we're going to do work on those comments in real time as they come in. But this allows us to take kind of a legacy code base or something that's a monolith or something that's older and has just a relational database sitting in the background, and allow it to participate and generate events that are then useful, right, as part of any company that's kind of looking into a streaming initiative. So this is like our kind of front page, where if you're going to look at your topics and browse around in our UI, this is just kind of an example of those topics showing up. You can see these last few, right? They're prefixed with DBZ for BZM, and we've got comments and options and all these different things, right? All these new topics that showed up. So we've got DBZM hooked up, and we're going to look at one of the comments, right, that's within that comments area. You can see right there, I'm okay with monoliths, right? And there's an author, and there's all this data, right, that came with the comment, right? And so all of that is now showing up in our topics, and we can action on it. We can do something useful with it. So if you haven't heard of Hugging Face, or if you haven't used it, it's a really great suite of tools. If you're into Python, it's a great tool for just like orchestrating and training and using machine learning models. They've got Hugging Face Hub, which has tons of models out there that can do everything from, you know, LLMs to generating images using Stable Diffusion, just whatever you want. And the awesome thing is that if you look here, it's a pretty, you know, I've got Kafka producers and consumers here that are all wired up and consuming. So when those messages come in, we'll action on them. But really, just all we're doing is instantiating a model and throwing this data at it, and then sending it back to the cluster on a different topic. Instantiating that model and using it is a couple of lines, and they've got a massive list of models that you can use right now. So we're using a sentiment analysis model, right? So what it's going to do is it's going to read that comment, what was it, like, I'm okay with monoliths, and it's going to interpret that as positive, right? And it's going to have a score, and that's its confidence level, right? How confident it is that that's a positive message. So we've gone from having kind of data in a topic. Now we've done some enrichment, right? We've actually got some insight into what that actually means. You could drive business analytics or have a dashboard or something like that that's counting these and say, in general, the sentiment for this post is positive, right? As people are leaving comments, or maybe it's negative, or things like that. You could do the same thing with all Twitter posts that that have a particular exchange ticker mentioned on it, or something like that. Oops, sorry. So that's kind of the quick journey that our data has kind of taken, right? It came from a legacy system. We brought it into a modern streaming system using Debezium or CDC, and then we did a little bit of machine learning on it, and we pushed it back into that topic. And I finished putting this demo together in June, and right about at that exact same time, our CEO made the announcement that we've acquired the company Benthos, and we have all these brand new amazing connect options. So certain aspects of this data, or of this demo, Debezium is awesome, and it's a little, there's parts and pieces and plugins to manage. But if you ever wanted to do similar connectivity things, taking data from databases, putting them into other, just about anything. I think we support more than 220 different sources and destinations. And there's also, I think it's a little bit funny because, we call it Redpanda Connect. Everybody talks about the connectivity options that are here, but there's also a super powerful processing layer sitting in the middle, which allows you to say, oh, I want this data, but I want it to look like this on the other end. And maybe you even want to go and talk to another data source and do more enrichment and bring something in and send more valuable data to another source. It's fantastic in the entire thing, the ingress, the processing layers, the output, it's all defined in a single YAML file. And in order to deploy it, you pretty much just, I'm sorry, I was describing without the slide up. But if you want to deploy it, you just type rpk connect-c and then pass it the YAML file, the location of the YAML file, and it will just spin up, right? And it'll launch a process, and it'll start connecting, to the source, to the input, and processing that data as you've defined it, and sending it to the output. It's really, really fast. It's awesome. Like, developers love it. It's rapid deployment, rapid change. It's easy to deploy because it's declarative. It's only a single file to configure the whole thing. And there's a lot, again, kind of like I was talking about before, there's other tools that are really big that do lots and lots of really advanced types of analysis and changes and things like that on your data. But they're very, very heavy. And this is really light. It's all wrapped up into a single Go binary. And like I said, there's only one configuration file, and this is it. So here's an example of that same data that we were looking at, right? We kind of dug in and we found where the comment actually was. And that was, I'm okay with monoliths, right? But inside that data, there was also an email address. Maybe before we send it on, we don't want to have that email address in there. Maybe we want to do some form of hashing or anonymization or something like that on the way. This is just done along the way, right? As we're shipping our data around. It's very, very simple, right? It's not super complicated. Or maybe just, in the example, right, on the repo that I created, if you look at it, it's actually just producing data back into the Redpanda cluster on a different topic. And so maybe you share credentials so that people can read the anonymized data as opposed to the source that has the anonymous data. Oh, here's the example, right? There's the author email, and it's hashed. So the other amazing thing that it can do is it can do aggregations. And I thought this was really clever when we first acquired it and it was first announced. I got to talk to the original developer. His name is Ash, and he was talking about how we actually do, because this is stateless, right? You can spin up a whole bunch of instances of it, and if any of the instances go down, or your cloud provider drops a broker or a node on you or something, they will continue to work. And I asked him how you can do aggregations statelessly, right? It doesn't really make sense. And he said it's all just managed by the consumer group. It's not going to mark any of those messages as recorded or as processed, right, in the consumer group until the window has actually lapsed. So if you monitor those topics, your consumer lag is going to be somewhere between what your window period is and what your window is and 0. But in that scenario, if you were to drop a broker or drop a node and spin up a new one, or another one takes over in the consumer group, it's going to go and read back through the messages that it missed because they weren't acknowledged by the consumer group. I thought that was clever just because, you know, it keeps all of those concerns about state. You're not really thinking about that when you're operating the Connect instances. So if that last minute announcement wasn't painful enough, this morning before I got on the airplane, we announced our best-in-class AI platform for developers. We call it Sovereign AI. And so that whole thing that we did with Hugging Face and sentiment analysis and all that stuff, we have just created the ability to, in a couple of lines here, actually send all of that data to a model that's running locally on the Connect instance that we're using, meaning that whole other app that I wrote that's consuming data and then doing sentiment analysis on it and producing it back to a topic can all be accomplished in a very, very brief section just like this. So it's hard to keep your demos up to speed with the rate at which we're releasing new features. So the next iteration of this talk, I believe, will probably have this worked into it to some degree. There's still value there. Technically, we're doing sentiment analysis, and this is just talking directly to a LLM, right, and asking it a question. So it's not the exact same use case. But I found it funny that, like, you know, I started a little early with my demo, or to prepare for my demo, and we've released features that have made it, made it a little redundant since then. So that's for the most part the kind of deep dive into some of the tooling, some of the other things in the ecosystem. If anybody has any questions or curiosities, obviously reach out to me on LinkedIn. Happy to answer questions. That's what I do. I'm a solutions engineer. I talk to people about great use cases, how to get connected, how to use the other tools in the Kafka ecosystem with our product. We have Redpanda University. We've got great docs. We have a super engaging community over on Slack. So always feel free to jump in there if you're going to go and be successful and use community. We have lots of people just in there being successful using Redpanda community full time, and it works great for them. And the community over there is helping support. We're open source as well, or we're business source, which means you can check out the code and read it and use it. And we also have a serverless option, right? So if anybody ever wanted to just like spin it up and get their hands on it and have an actual production ready version of Redpanda, it's a pay-as-you-go model, right? Just for megabytes and partitions that you consume. Okay, it's a bit of a monologue. I'm happy to entertain any questions. If anybody has any questions about anything that we covered, whether it's Redpanda or any of the examples of, you know, Debezium or Hugging Face or machine learning or any of our new Connect features.
Thank you, Brian. Any questions?
So the question I wanted to ask is, when you talked about the different deployment models, you kind of mentioned the bring your own cluster. And I was wondering if you could talk a little bit about how that works with the Redpanda Connect with like the machine learning, you know, if a company has their own in-house models that they want to use. If you could talk a little bit more about that.
Yeah, so this is like super early days. Like I said, we acquired Benthos in June, right? Which is now we're rebranding it as Redpanda Connect. So specifically what models we support, I know that in this example, we're highlighting what the model is, and my guess is that it actually has to be sitting on the file system of the node that's running. We have not integrated any of this into the cloud offerings that we have currently, and that is like right around the corner. So I don't even know what those things are going to look like just yet, but it's going to be pretty cool, right? If you can go into a managed user interface and take one of these YAML files, right? And I imagine there's lots of other tooling for Benthos, right? Before we acquired it, for writing these YAML files, because they can get pretty extensive, right? If you're doing lots of transformations or things like that. So I think that we're going to have some type of assistance or GUI that's going to help you kind of compose these and connect things up to your different data sources and things like that. But the short answer is I don't know exactly what the ML piece is going to look like because it is shipping a big binary around, and there's a lot more to come on that front, right? They, like I said, they announced it this morning, so I think there's going to be a lot more announcements around not just using models, right, but building them and things like that. So ai.redpanda.com is the place to kind of stay up to speed on that subject. Does that answer your question?
Yeah, thanks for the presentation. I have like a question where in one of the slides you spoke about running the UDFs within the broker itself, like having a how does it work? Like how do we differentiate between the resource profile of the UDF with the broker, as well as if there any failure happens during the execution of the UDF? Will that affect the message processing? There was a slide on the.
Sorry, can you speak up just a little bit? I lost the.
So there was a slide on the in-house UDF or in-place UDF.
UDF?
Yeah, somewhere in the earlier slides before.
Oh, yeah. So on the next stuff. One of these?
No, not this. I think like in the earlier slides. Yeah, data.
Oh, transforms. Okay, sorry. Yeah.
So if any one of the transforms, these transforms runs within the broker itself.
Yeah, exactly.
So how would you like to let's say if any of these transforms fail, like how will you report that back to the user, or will that affect the messages being pushed into the broker?
Yeah, there is logging. The actual so it's easier right now to run self-hosted, right? If you were going to use our enterprise product, we're currently limited availability on this feature in our cloud product for reasons like that, right? You can go in and look on your brokers and you can find where something would have failed. We're emitting certain metrics and things like that, but we haven't presented those in our cloud UI yet. And so the kind of the best way to do it, frankly, is to spin it up and monitor the brokers yourself right now. And most of the time, when you're developing against it, people will do that in a compose file and kind of operate locally. But if you're going to debug them in production, it's log files and metrics.
Thank you. Another follow-up is that, like you mentioned initially, that this was written in C++, but the user-defined function is in Go. How does that interplay?
Yeah, so I don't know for Rust. I believe Rust, since it's just compiling to a binary, is just going to be run as a binary. If you want to write a new function, you would use RPK and it will kind of stub out a little project for you. And you can go and just put your function in there and then use the command line to compile it and push it back into the cluster. For Go, we're actually, I don't know if you're familiar with Tiny Go, but it's a small Go implementation. I believe we implement it per core. But the user experience is the same, right? You write your code, and then using our tool, you would push that onto your brokers, and then it works from there.
Okay, thank you.
Yeah.
Any more questions from the audience? I think we have one question online. Does Redpanda use Zookeeper in the background?
Famously, no, we do not. That's one of our claims to fame. Is on the left here, you've got all your different parts and pieces. Also, not pictured as cruise control for the continuous balancing of partitions and things like that. Our brokers, other than Connect, right, which is the new thing, our brokers are the only role that's running, right? If you even with built-in schema registries and proxies and things like that, the brokers are all democratically electing leaders of partitions amongst themselves using the rules of Raft, the Raft consensus algorithm.
Any more questions? No, thank you, Brian.
Thank you so much.
Great
Everyone.
presentation. Next, we have Harsh and Kshitij. Sorry if I butcher your name. From ORP. You want to guys set up here, and I'll introduce you meanwhile. In this talk, engineers from ORP will talk about the stream processing and query challenges of implementing a usage and spend alerting products feature at the scale of millions of events a second. ORP powers billing for some of the world's fastest growing infrastructure companies, including Vercel, Replit, and Pinecone. In Orb, you can set up metrics that determine the basis of consumption charges for your customers and set up alerts that trigger as a result of customer spend. This translates to an invalidation architecture problem with some serious challenges to maintain correctness performantly, especially when allowing extremely flexible metric definitions. Second. Jitesh is a co-founder and CTO of Orb, the billing platform for the fastest growing infrastructure companies. Prior to founding Orb, Jitesh was an engineering leader at Asana. He received degree in computer science and philosophy at Caltech. Take it away.
Thanks everyone for attending the talk. I'm Jitesh, as so kindly introduced, one of the co-founders at Orb, and this is Arsh, who works on our infrastructure team. I'm going to set a little bit of context around Orb, just to have the rest of the talk make sense. We'll get through that portion pretty quickly. It's not a sales presentation for Orb, and then Arsh will dive deeper on the specific topic for this talk, which is how we build a solution around real-time alerting. So real quickly, just to set some context, I was previously Asana. Asana, like many other companies, spent a bunch of engineering time on billing. They ended up basically wrapping an existing billing vendor in-house. After leaving Asana, wanting to work more in that monetization space, we saw that existing billing solutions really weren't built for infrastructure companies, where there's a kind of billing challenge as well as a data infrastructure challenge with having to aggregate a bunch of data as well as power workflows reactively on top of this data. So some of the technical challenges that any company might face, whether or not Orb is in the picture, there's a lot of complex business logic, especially when it comes to things like prepaid credits and discounting and ramping over time. So this is really the domain logic of billing itself. When you're doing something like more dynamic billing, you have to provide customer visibility. This is often not a huge concern when you're just billing based on seats because it's pretty static. But these days, if you're a customer of Redpanda or any other usage-based system, you want to be able to know how much you've accrued this month in some sort of billing dashboard. When you're making pricing changes, you want to be able to do that across all your customers, and this gets a lot more complicated when there's a dynamic element involved. And then, of course, there's the actual data infrastructure to be able to capture and aggregate that data. And finally, this is sometimes not super obvious to the product and engineering teams we work with, but specifically usage-based billing makes your accounting team's life much harder because it changes the way that you're recognizing revenue. So here's what Orb does. We take in a bunch of raw usage events. Within the platform, you configure basically aggregations, and I'll show you that in the form of metrics, plans and pricing, in order to determine how you're going to translate those $2. And then at the end of the day, we generate invoices, deliver those invoices. We have a native invoicing product, as well as provide financial reporting on top. So I'm going to skip through these slides and just do a quick demo. And I'll kind of set the stage for Arsh, because I'll show you the alerting feature within the platform, and then Arsh will talk a little bit more about the technical stuff of how we built it. So here's Orb. This is demo.withorb.com. So you don't have to talk to a salesperson or me to go see this. Typically, the place we like to start is events. Again, events are pretty unique to usage-based billing. You probably won't have events in a traditional billing system, but an event is pretty simple. It's just a dictionary of customer attribution, timestamp, and properties. So these events represent product usage happening in your application. Obviously, will depend a lot on what your application does, but could be an API request, could be a compute heartbeat, a transaction processed. Really depends what you're trying to measure and how that might eventually translate to billing. But the important thing to note is events do not just contain a quantity. They can be queried in the platform on top of some key value pairs. So great, you send in events. Just for context, and this is part of the infrastructure challenge at Orb, is people are sending us events on the small side at maybe hundreds of events a second, ranging to almost 1 million events a second on single tenant. So lots of variability depending on your business and what you're actually measuring. So you send in events, and then on top of that, you configure a metric. You can do that in like a BI style interface that probably everyone has seen, where you're configuring some filters and an aggregation function. But you can also just do that with SQL in the platform. So this is, again, one of the things that makes doing things like alerting hard, because you have the full flexibility of SQL. And then to be able to performantly compute those alerts gets tricky, but maybe we'll show you that in a second. This is the way that you're actually taking those events and building a thing that you're going to then associate to a price. So the very simple thing could just be counting API requests. So finally, you construct a plan, which is like your pricing catalog on top of those metrics. And the so what of all of this is, if I click into one of these demo customers, this is what you see. So this is a specific customer subscribed to your professional plan. Here's how their usage has trended over time. And then the invoice looks quite different because it's not just 3 quantities on a PDF. We show you the usage data. This is the internal view of the invoice. And as I was saying, we have a external facing invoice solution as well. So this is what your customer would see using a solution like Orb. So the final piece I want to get to is the alerting piece. So this is the context for the rest of the technical talk. Lots of people want to be able to set up alerts in the platform, and an alert lets you get notified when one of your customers hits a specific usage threshold or a cost threshold. So you've probably seen these in some usage-based products you use, but typically this would be powering something like a workflow internally where someone on customer success reaches out to that account, or it could be powering a workflow externally like an email just to notify the user, or even just to like shut off their project. So lots of different use cases that come downstream of this alert. I think that's all I want to show in the product. So maybe we'll dive into the more technical piece on the actual alerting.
Cool. Thank you, Shatej. Hope everyone's doing well today. So I'm going to talk specifically about how we support low latency alerting on high cardinality usage data sets. But before we specifically get into the how, I want to really hone in on the why. With specifically pay-as-you-go products, there's at least 3 use cases that I really like talking about when we talk about alerting. So one, as a buyer of a usage-based product, one thing I'm always concerned about is like, oh no, I misconfigured something and I now have like a $100,000 bill for something I don't want to pay. So you see this on Twitter pretty frequently, but it's really important for me as a consumer to be able to say, I don't want to spend more than X dollars. And if I hit that limit, please just like, let me know so I can do something about it. On the other side, I think some contracts will have this kind of baked into them where customers and sellers will say, great, you want to buy $10,000 of my product, that's fine. But once you use up all $10,000 worth, I'm going to have to cut you off. And anything over that, I'll just eat. So in this specific case, we really want to protect the seller downside so that they can know to cut out product access as soon as possible when you hit that threshold. And then the last one is kind of more on the enterprise side, where you really want to be able to trigger upsell motions if one of your customers is able to go, great. If one of your customers is able to hit kind of what they've committed to as part of their allocation. You don't really want to be cutting off product access for them, but you also don't really want to be eating those infrastructure costs. Cool. So to dive into this a little bit more, and Shitej has touched on kind of all of this, so I'm going to not spend too much time, but the core concepts we're going to need for alerting specifically, the first is some sort of metric, and a metric is basically just some SQL query that runs over a set of events and will output a specific quantity. These metrics will eventually get combined with rates and put into plans. Plans will be subscribed to customers, which will generate invoices. Your invoice will basically just have kind of the metrics computed quantity times the rate, and that'll give you basically your accrued total. We allow configuring alerts on either like the accrued invoice total, which is like the cost alert, or a specific metric. So for example, if you've committed to 10,000 units of usage on this specific SKU, we support that using kind of a usage alert. And then the last key point here is totals for the usage or totals for the accrued invoice only really change when we receive a new event for a customer. Cool. So I'm not really going to spend too much time here, but let's put ourselves in the shoes of a database company, and we're going to build on egress and ingress. So maybe we'll set up a specific SQL metric for egress that just sums over gigabytes in our events. We'll put this into a plan. So we'll have an egress price, which just has a unit rate of 0.5 cents per gigabyte, and an ingress price, which is actually a tiered or like a stair step price, where the first 1,000 gigabytes will cost you 10 cents, and anything after 1,000 will cost you 20 cents. Now, if I subscribe to this specific plan, my invoice might look like this for the current billing period. Looks like I've used about $40.80 worth of usage. Now, as a customer, there may be a couple of things here I want to do. Like one, for that ingress price with the tiered pricing, I may not really be willing to pay 20 cents a gigabyte for ingress. So I'm going to set up notifications that say, hey, when I get close to that kind of limit, please let me know. So I'll set up usage alerts on that one metric at 800 and 1,000 units. And then I'm pretty price conscious, so I don't really want to spend more than $150 any given month, because that's just my budget for this specific tool. Yeah, and then the last thing that I really want to hammer in on is kind of events are the only things that can change invoice totals. So for that egress price, if we receive an event that looks like this one down here with 10 gigabytes of usage, we know that this is going to increase the cost of this invoice by 5 cents. Cool. So how do we actually build this? Well, naively, if I just wanted to kind of get something out there as an MVP, we're like a small scrappy startup. Let's put all the alerts in a table. Let's put some sort of timestamp on that table, and let's build a evaluation service that will pull that table, take the oldest computed alert, recompute it, and determine whether or not we need to fire a specific alert or not. Cool. So that's exactly what we did, and we put that in the context of our whole system, and it looks a little bit more complicated now. But the main pieces to note are on the right side. We have some services that all rely on usage. So we have an invoice updater whose main responsibility is to kind of periodically go in and refresh these invoice totals. What that'll do is it'll pull off of the invoice table. It'll make a request to our metric computation service, which will compute these metric values. And then it'll go and populate some cache. And the alert evaluation service will do roughly the same, but instead of populating the cache, it will determine whether or not there's an alert to fire. One interesting thing here is that you might look at the metric computer and realize that not all alerts require us having to go back to the data store. That's because if you think about usage, it kind of really only happens around right now. So after a specific period of time, in our case, it's about a day. We don't really need to go back and recompute data for older timeframes, because that's typically not going to change. Cool. So this is V1 of alerting. As you can imagine, there were quite a few pain points here, but maybe a few to talk about specifically. The first was wasted work. So if you're just pulling through a table, a lot of the customers we're processing, we have no idea whether we expect anything on their from like the alerting side to actually change because we don't know if we've received an event or not. Over time, as we have more alerts and invoices on the system, we expect that our smaller tenants who may only have, hundreds or a few thousands of customers will have to now start waiting in this much longer queue to get reprocessed over and over. And we're also duplicating a bunch of work on like the metric computation side between the invoice updater and the alerting service. So to address this kind of these pain points, we decided we really need to move. We decided we really needed to move closer to the 21st century and work off of an event-based model and start thinking about invalidations and figuring out what is actually a useful amount of work for us to be doing and at what point. So one of the things we know is that when an event comes in, we can expect some sort of material change to happen to that customer state. So that's probably roughly a good time to start reprocessing that customer. So that means, reevaluating their alerts, recomputing their invoice, and so on. So what we kind of talked about at a high level was we'll have like a 4-component model. We'll have an invalidator whose responsibility is to figure out what set of customers we need to be reprocessing. We'll have a scheduler that will actually be responsible for going from these invalidations to figuring out when we should be reprocessing them. We'll have a queue that we can actually use as a persistent data store to manage kind of the jobs that we have to work on, which are the customers we have to reprocess. And we'll have a set of workers that will be able to actually go ahead and reprocess all of these customers. Diving a little deeper into the invalidator here. So the input is just the events that are being ingested into our events data store. And the output should be some sort of customer times like a time of invalidation. What we decided to use for the time invalidation is just the current wall time, which ends up working just fine. One important thing to note here is that we use Druid as our events data store. So our ingestion into Druid is also a Kafka topic. So all we had to do here was spin up a new consumer group on the same topic. And that way we were able to get basically every single event that goes into our data store. Next, we'll talk about the scheduler. So the scheduler is downstream of the invalidator. It's responsible for taking a bunch of invalidations and determining whether there's any work we need to schedule or if we can just no-op this specific invalidation. So the input here is just the invalidation output of the invalidator. And we go ahead and basically update some queues somewhere to say, hey, can you please process this customer? In a lot of traditional systems here, you might think that you can go directly from the invalidator to the worker, and that is absolutely true. That is a workflow we had considered, but one thing we realized specifically about our customers' ingestion patterns is that when one end customer does some work on our customer's product to generate an event, shortly after, we're probably going to see multiple more events coming in. So if we eagerly reprocess the customer on the first event, we're going to end up just spinning and refiring and reprocessing the customer again and again until we've cleared that like one period of usage for that customer. So instead of doing that, to eliminate some, not necessarily duplicate work, but to eliminate some load on our data store at the cost of like alerting latency, we ended up building a time-based batching mechanism, which basically just says, great, have we seen this customer recently? Have we already scheduled a job for it? If not, instead of scheduling a job for it to be reprocessed now, let's bake in a little bit of a delay so that if we get more events, we can just drop those. And we just call this collapsing invalidations on our end. And the last thing we have to talk about is the queue here. So the queue is obviously responsible for storing the set of work that needs to be done at any given point in time. All of our processes are scoped to a customer. So we basically just have like a customer ID, as well as the next computation time, as well as some other timestamp fields that really help us observe and monitor the health of the system in terms of the alerting lag, as well as how many customers are being invalidated at any given point in time. One thing that was required for the queue here was the ability to schedule jobs into the future. Because of that time-based batching mechanism, we couldn't just send a message down a Kafka stream and say, great, that'll get picked up in 10 minutes, because that's not really the guarantees you get from Kafka. We also needed the queue to be transactional, because as a billing company specifically responsible for preventing your customers from having $100,000 bill when they expected $1,000 bill, we couldn't risk dropping an invalidation. So we decided to put the queue directly in Postgres. So putting it all together, it kind of ended up looking like this. So we have our Kafka topic for the events coming in. That obviously gets ingested directly into our events data store, but it also gets consumed from the invalidation service. The invalidation service will wait for a batch of events to be persisted into Druid because of that asynchronous nature of Druid. Druid ingestion, we need to ensure that we are consistent when we fire the alert. We'll then output a set of invalidated customers on a new topic. The scheduler will pick these up. It'll go ahead and schedule customer processing for any customers that need to be processed. It'll drop any invalidations that we don't need to reprocess at this point. And then we have our worker process the customer processor. This will just go ahead, queue the Postgres table and do some work. The nice thing about this architecture here is that each one of these pieces is individually scalable. So if we realize we're falling behind on the invalidator, all we have to do is repartition the events topic and scale up the invalidator. If we're falling behind on actually processing the customers, we can go ahead and scale up the worker processes. One thing we realized with this approach is that we're able to do a lot of high-level optimizations to do the right amounts of work. But one thing our customers still really wanted was basically, hey man, I got like 10 enterprise customers. I want to give them 10-minute alert lag. I know I have 2 million other customers, but is there anything you can do about this? With kind of this event-based architecture, it's very easy to fork off of this and build your own priority queue very quickly. So that ended up taking us about a week to build for our customers, whereas the architecture probably took a couple months. Cool. So in terms of kind of what we realized in terms of wins from this, there were mainly three. Alerting latency, generally this dropped about 60% across all of our tenants. For sparse ingestion customers, this dropped about 95%. We also eliminated the starvation problem for small tenants because we were able to just queue up their customer processing relative to their own customer base, as opposed to being relative to Orb's total customer set. And we also unlocked new future scaling projects. So one of the things that we're currently working on is, instead of having to ever recompute all of these metrics from Druid, our events data store, we want to build next to the invalidator an incremental metric computer, keep these running totals in memory, and directly off of the cache, we want to be able to determine, great, we have high confidence this alert is ready to fire. Let's go trigger the full pipeline for this immediately. And our estimates here are that we can probably provide real-time alerts here under a minute. Cool. Thanks, guys. And then
Yeah, we're hiring, but happy to take questions.
Thank you, guys. Any questions?
This looks a lot to me like an incremental view maintenance problem. So why doesn't incremental view maintenance solve the problem you have? Incremental view maintenance. So you define the table that you show to your customers as a view, which is maintained incrementally using a set of queries.
Yeah, I think we've tried approaching the problem like that. It was a couple tricky parts about that. One is some of these views are really, really expensive to maintain because, again, we allow writing arbitrary SQL. So we're just running some performance problems with prototypes of that implementation. The other thing is the query itself looks very different, even for all of the subscriptions that you might have. So for example, if you cancel a subscription mid-period, or you just have customers with different time zones, the actual thing you're evaluating and the time range on which you're evaluating it looks very different. And I think that basically causes all of the, at least prototyping we've done, to explode in the amount of work it needs to do to maintain that view. But I guess maybe to the broader point Alex was mentioning at the end, we are looking into ways to specifically maintain some subset of these alerts in an incremental way. So for simpler things like sums and counts, we don't need to be querying over the whole billing period. We can just incrementally maintain those results, and that's the path to the sub 1 minute SLA alert.
Thank you. Any more questions? All right. Thank you very much, guys. Thank you, everybody, for coming. The recording will be available at YouTube, and we'll send the update. Thank you. You're